Hi there. I'm glad you're here in this little pocket of quiet. Outside, the sky holds its usual stars, scattered and distant, but one of them shines with a strange, steady brightness just after sunset. We call it the evening star, and it looks gentle enough to wish on. Tonight, we're going to move a little closer to that light and ask a softer, sharper question. How can something that seems so calm from here be one of the most dangerous worlds in our entire solar system? We'll wander above its cloud tops, listen to the slow churn of its heavy air, and trace the hidden forces that turn this bright point in the sky into a place of crushing heat and peril. No rush, just a quiet conversation with a beautiful, deadly neighbor. And if these slow journeys into the dark help you feel a little more at ease or a little more curious, a gentle like and a soft subscribe can help others find their way here too. Tonight, we'll drift together and let Venus come into view. Far out in the darkness, not every world has felt our close attention. Out near the edge of the familiar, Uranus and Neptune circle the Sun in long, slow orbits, so distant that sending even a single probe is like trying to mail a letter to the edge of a vast, dim field. If you imagine the distance from Earth to the Sun as a single long step, Uranus waits almost 20 such steps away, and Neptune nearly 30. So far, only one spacecraft has ever swept close past both of those pale giants. NASA's Voyager 2, gliding by just long enough to take a few careful looks before it was flung onward into the colder dark beyond. Closer in, another kind of difficulty appears. Mercury, the innermost planet, seems like it should be easy to reach. It is right there, hugging the Sunday. But the Sun is not just a lamp at the center. It is a deep well of gravity. Any probe that falls inward feels itself pulled faster and faster. To meet Mercury gently instead of racing past it, a spacecraft has to follow a winding, patient path, looping around in long curves, so that the Sun's pull does not simply grab it and fling it away. In the 1,970 seconds, the Mariner 10 probe traced such a path, flying past Mercury and sending back the first close images of its battered surface. Decades later, another spacecraft, Messenger, finally managed to settle into orbit, circling that small, scorched world again and again. Each mission was a reminder that close in space does not always mean easy, and that even the smallest changes in distance from the Sun can turn a simple journey into a careful dance with gravity. Venus, on the other hand, tells a different kind of story. It is our nearest planetary neighbor, bright in the evening and morning sky, and the path to it is more straightforward. Compared with the trek to the outer giants, or the tricky descent toward Mercury, sending a spacecraft toward Venus is like crossing a quiet street. The launch windows are kinder, the travel time shorter. On paper, it should be one of the simplest worlds to approach. But Venus hides behind a thick, unbroken veil of cloud. To even an attentive telescope, its surface is a secret, wrapped in creamy light. Beneath that smooth appearance, the planet keeps conditions so harsh that metal softens, electronics falter, and any fragile machine from Earth begins to fail almost as soon as it touches down. The Russian Venera landers were the first to reach Venus's surface, dropping through the heavy atmosphere like seeds falling through deep water. They survived there only for minutes, tasting air dense enough to crush, heat hot enough to melt, and a landscape where rocks sit in a permanent oven, baked from all sides at once. Long before we could send those metal messengers, Venus already played a quiet role in our understanding of the solar system. Roughly twice in every century, from the vantage point of Earth, Venus passes directly between us and the Sunday. For a few hours, its small, dark disk slides slowly across the Sun's face. This rare event is called a transit of Venus. In 1769, astronomers around the world waited for that transit with clocks ready and telescopes aimed. They knew that if they could time Venus's passage across the Sun from different places on Earth, they could use the slight differences in their measurements to calculate something far larger. The true distance between Earth and the Sunday. That number would act like a master key. With it, the whole scale of the solar system could be drawn more accurately, and long ocean voyages on Earth could be navigated with far greater confidence. Nearly 2 centuries later, in 1961, the Soviet Union sent the first dedicated probe toward that same bright world. It was called Venera 1. The plan was simple in spirit: send a small spacecraft past Venus and listen carefully to what it had to say. Venera 1 did pass Venus as intended, becoming a quiet pioneer of interplanetary flight. But its voice faded too soon. Mission Control lost contact with the probe before it arrived, and the small metal traveler finished its journey in silence. The following year, the United States tried to send its own message to Venus. NASA's Mariner 1 rose on a column of fire, carrying with it lines of code that were meant to guide it safely out of Earth's embrace and into the long curve toward Venus. But somewhere in those instructions, a tiny flaw had slipped in a missing mark, an error so small that it could be hidden in a character or two. In the delicate balance of guidance and control, that was enough. Soon after launch, the rocket began to misbehave, drifting from its intended path. Controllers watched their screens as the numbers wandered, realizing that the spacecraft was no longer where it was supposed to be. In the end, there was only one safe choice. A destruct command was sent. High above the ocean, the promising arc of Mariner 1 ended in a brief, bright bloom of scattered metal and burning fuel. On the ground, there would have been a deep, hollow quiet in the control room, the kind that settles in after months of work vanish in seconds. Opportunities to launch toward Venus do not come every day. Because Earth and Venus circle the Sun at different speeds, there are only certain moments, roughly every 18 months, when the geometry lines up just right and the path between the two worlds becomes especially efficient. Missing one of those windows can mean waiting a year and a half for the next. NASA, unwilling to lose that chance, had a second spacecraft prepared, Mariner 2. Mariner 2 was, at heart, a redesigned Ranger spacecraft, a type originally intended to go to the moon. The Soviet Union had already scored a series of dramatic firsts, and the United States felt the pressure keenly. Engineers at the Jet Propulsion Laboratory worked within short lead times, adapting designs and accepting that some imperfections would have to ride along. The Ranger missions to the moon had all failed so far. Now a cousin of that same design was being asked to do something even more ambitious: leave the Earth-Moon neighborhood entirely and find its way to another planet. In August 1962, Mariner 2 rose into the sky. The rocket stages separated, the protective panels fell away, and the small spacecraft unfolded its solar panels like delicate wings. At first, things did not go smoothly. The transmissions reaching Earth were weak, and a subtle anomaly during launch had left it drifting off course. For a week, it flew like that, a fragile machine carrying our questions toward the inner solar system, but not quite on the path it needed. On the ground, engineers calculated a complex correction, a sequence of motions that would ask the spacecraft to roll, then pitch, and finally fire its main engine for just the right length of time. The commands were sent, a string of radio whispers crossing millions of kilometers. About an hour later, far from human eyes, Mariner 2 turned. It rolled, it pitched, and then its engine burned. When the maneuver was done, its trajectory had shifted. The new path would carry it close by Venus, threading through space with a little more certainty. The relief did not last long. Only a few days later, the spacecraft lost its lock on the Sun, and on Earth, the two beacons it used to orient itself. For a time, it no longer knew exactly which way it was facing. Before controllers could fully sort out what was wrong, Mariner 2 recovered on its own, slowly turning until its sensors could once again feel the Sun's warmth and Earth's faint radio call. Its signal strength climbed back to normal, but a short circuit in one of its solar panels left it with less power than planned. Instruments flickered, telemetry channels failed one by one. Inside its metal body, heat began to rise. At that moment in history, no one had yet succeeded in sending a working probe past another planet and receiving a full set of data in return. Both superpowers had launched small machines outward, and all had met with silence, failure, or only partial success. Mariner 2 joined that uncertain procession, limping along, losing some of its sensors to the harshness of space and struggling with its own rising temperature. Yet still it flew. As it drew closer to the Sun, something simple but important changed. The sunlight grew stronger, and even with one damaged solar panel, the spacecraft could gather enough energy to keep its heart beating. Day by day, kilometer by kilometer, Venus grew larger in its field of view, not as a shimmering jewel, but as a pattern in the codes and numbers flowing back to Earth. Finally, Mariner 2 swept past the planet, skimming at a distance of a little less than 35,000 kilometers above the hidden cloud tops. From that vantage point, it could not see the surface directly, but it could listen and feel in other ways. Its instruments searched for a magnetic field strong enough to shape the space around Venus, the way Earth's field shapes the flow of charged particles near our world. They found no clear sign of such a protective bubble, only a quieter interaction with the solar wind. Other sensors measured the heat spilling upward from below those bright clouds and found that the entire planet seemed to glow in infrared like a banked furnace. Temperatures across Venus reached toward 500 Kelvin, hotter than an oven in a home kitchen, hot enough that lead would soften and many metals would weaken. From far away, Venus still seemed gentle, a pale lamp in the dusk, steady and calm. But as Mariner 2 limped past its cloud tops and sent home its thin stream of data, a very different picture came into focus, a world wrapped in dense haze, with little magnetic shelter, its surface held in a constant grip of crushing pressure and relentless heat. The small, troubled spacecraft had still managed to whisper something unmistakable about our nearest neighbor. Beneath that soft evening glow lies a place every bit as dangerous as any world we have ever known. With that in mind, the idea of actually touching down there felt like another kind of leap. A brief flyby high above the clouds had already hinted at the brutality below. Imagining a fragile lander on that surface was like picturing a snowflake resting on the floor of a furnace. For the moment, though, the United States chose to rest just a little in the glow of what had finally gone right. Mariner 2 had become the first truly successful interplanetary probe, the first small machine to leave the Earth-Moon neighborhood and return a clear, sustained story from another planet. In California, at the home of the Jet Propulsion Laboratory, People who had watched incomplete data, weak signals, and failures now had something simple and shining to hold on to. They had done something the Soviet program, with all its early triumphs, had not yet done. For a night or two, there would have been coffee that tasted sweeter, laughter that came more easily, and a sense that the long, anxious hours had been worth it. While America took comfort in that first success, the next bold steps toward Venus came from the other side of the world. The Soviet Union turned its attention not just to passing by the planet, but to trying to reach its hidden surface. The goal of the Venera series was quietly audacious: to send landers all the way down through the crushing air, and to have them survive long enough to send back real measurements and, if possible, actual images. The designers understood that they were not building gentle surveyors for a mild world. By then, the emerging data suggested that the temperatures at the surface of Venus were high enough to melt lead, and that the atmospheric pressure there was dozens of times greater than the pressure at sea level on Earth. Any structure that touched that ground would be squeezed from all sides and baked from within, like an object dropped into the deep of a hot ocean. The landers they sketched and refined began to look less like sleek rockets and more like heavy diving bells, rounded and reinforced, meant to endure for minutes in a place where hours were out of the question. In June of 1967, Venera 4 rose from the launch pad and headed for that shrouded world. The spacecraft was made of two main parts: a carrier bus equipped with instruments to study space and the environment during the trip, and a spherical descent module, a tough little capsule able to communicate on its own once it detached and fell into the Venusian atmosphere. When Venera 4 reached its destination and the descent module separated, it slipped into the upper layers of the thick air like a glowing bead dropping into honey. Its parachute opened, spreading fabric against the dense atmosphere, slowing its fall into something more like a drawn-out sink than a plunge. As it descended, the probe measured pressure, temperature, and the chemical makeup of the air, and sent those readings back in a steady stream. For 93 minutes, that tiny sphere talked, its voice traveling across the void to radio dishes on Earth. Then, while it was still about 28 kilometers above the surface, the signal simply stopped. At first, it was natural to imagine that the lander had been overwhelmed, that the heat had finally surged past its defenses, or the pressure had crushed its shell, but later analysis showed that its electronics had not yet been cooked. The descent module had done something more ordinary, and somehow more poignant. It had simply run out of power. Its batteries were empty. In those last minutes of its life, its instruments had been measuring an atmosphere that was already brutal. Extrapolating from those final readings, scientists estimated that on the surface itself, the temperature reached around 500 degrees Celsius, and the pressure climbed to roughly 75 times the pressure at Earth's sea level. The numbers were not just high, they were far beyond what most had expected. The Venera program responded as if preparing for a deeper dive. Engineers strengthened the next generation of landers, thickening walls, reinforcing joints, and improving seals so that heat and pressure would take longer to seep in. They also chose to fit smaller parachutes. In such a dense atmosphere, a broad canopy slowed the descent too much, leaving the probe hanging in the punishing layers for too long. A smaller parachute would let the craft fall faster, spending less time in the worst of the heat before reaching the ground. Venera 5 and Venera 6, launched in January 1969, descended into Venus with those refinements. They were able to learn more about the chemical composition of the atmosphere, sampling gases as they fell. Each contributed another line or two to the growing picture. An air thick with carbon dioxide, laced with clouds rich in acidic droplets, an environment that was not just hot and heavy, but also chemically harsh. Still, neither probe lasted to send a long report from the surface itself. Their lives were brief, their words cut short by the same unforgiving conditions that had ended Venera 4's transmission. Mission by mission, the Venera series kept inching forward. Each new probe carried slightly better heat shielding, sturdier structures, improved instruments, and more carefully planned descent profiles. None could hope to live for days down there, but each was designed to buy just a little more time than the last. In those short, intense intervals between entry and silence, more and more was learned about the winds, the layering of the atmosphere, and the strange, slow world hidden beneath the clouds. By 1975, a new design was ready, Venera 9. This time, the Soviet mission would not only send a lander, but also place a spacecraft into orbit around Venus. The orbiter would carry its own instruments to study the planet from above and, crucially, would serve as a relay station, catching the faint radio signals from the surface and passing them on to Earth with greater strength and clarity. 4 months after launch, the pair approached their destination, the orbiter and the lander, still encased in its protective spherical shell, separated in space. The lander began its fall toward the planet, while the mother craft performed the maneuvers needed to slip into orbit. In doing so, it became the first probe to circle Venus, tracing a path that allowed it to photograph parts of the surface in ultraviolet light, a wavelength that can sometimes tease out patterns hidden to ordinary human eyes. The new lander carried another important change. Instead of relying on a parachute all the way down, it was equipped with a ring-shaped aerodynamic shield that could help control its descent during the later stages. In the dense lower atmosphere of Venus, such a structure could provide enough drag to slow and stabilize the fall without the complexities and vulnerabilities of a large fabric canopy. It was a way of letting the thickness of the air itself help to cradle the probe on its way down. When Venera 9 finally reached the surface, the lander did something no machine had done before on that planet. It sent back pictures. Grainy and in black and white, the images showed fractured rocks and a horizon curved by the lander's own optics. A real landscape, not just an imagined one, emerging from beneath a sky that had remained closed to human sight for so long. There was, however, a flaw in the design. The lander had been given 2 cameras, each with its own protective lens cap. One cap came off as planned. The other stayed stubbornly in place. Half of the intended view remained blocked. 3 days later, and roughly 2,000 kilometers away on the Venusian surface, a twin craft, Venera 10, touched down. It too took images. It too suffered from the same small but stubborn problem. One lens cap did not eject. Even so, both landers had already achieved something extraordinary simply by being awake and functional down there at all. To give them that slim window of wakefulness, the spacecraft had been pre-cooled. While still in the chill of space, their internal structures brought down to temperatures much lower than they would naturally rest at. Once in the atmosphere, and later sitting on the ground, circulating cooling fluid carried heat away from the most sensitive components as long as it could. On the surface, where the ambient temperature would have tried to rush in like a tide, this cooling bought them time more than an hour of operation on a world where the surrounding environment was always leaning hard in the direction of failure. The story did not end there. In 1983, 2 more Venera craft arrived at Venus, this time equipped with synthetic aperture radar. Ordinary light cannot pierce the planet's perpetual cloud cover, but radar waves, with their longer wavelengths, can slip through, bounce off the hidden terrain, and return with whispers about shape and texture. Over the course of about 8 months, these orbiters patiently traced path after path, building up the first serious maps of the planet's surface beneath the clouds, from the North Pole down to about 30 degrees north latitude. From those efforts, the bright, smooth disk of Venus on the outside began to resolve into something far more complex within: highlands and lowlands, plains and fractured regions, the marks of old volcanic flows, and deep, ancient upheavals. Each line of radar data was like a blind hand learning the contours of a face it had only guessed at before, turning a featureless glow into a real, rugged world. And while those silent images were being drawn in distant control rooms, countdowns for other missions were beginning elsewhere. New voices preparing to join the long, patient conversation with this beautiful, inhospitable world. For a long time, when it came to Venus, NASA had been more of a quiet observer than a lead actor. The early bold landings and the first hard-won photographs from the surface had come from the Venera craft, falling through the clouds under Soviet flags. The United States had its early triumph in the form of Mariner 2, but after that, much of its attention wandered for a time toward Mars, toward the outer planets, toward the wider and colder reaches of the solar system. Then, in 1989, under the bright lights of a Florida launch pad, the Space Shuttle Atlantis lifted from the ground, carrying something small and focused tucked away in its payload bay. That stowaway was Magellan, a compact spacecraft with a very specific mission: to go to Venus and, like the Venera orbiters before it, use radar to peel back the planet's permanent cloud cover and reveal the shape of the world beneath. It was the first time an interplanetary probe had been launched from the shuttle, the first time a spacecraft bound for another planet had begun its journey, not atop a tall, slender rocket, but from the cavernous back of a winged orbiter gliding into space. When Atlantis reached orbit, the bay doors opened like a slow yawn, and Magellan emerged into the darkness, released to the quiet pull of the Sunday. A separate rocket stage nudged it onto the long path inward. Over the next 15 months, the little craft drifted toward Venus, carried along in an invisible arc, far from the noise and brightness of its departure. Magellan itself was a kind of patchwork child. To keep costs down, it had been assembled from spare parts and leftover components from earlier NASA missions, pieces that had once been designed for other spacecraft, other goals. Now brought together and given a new purpose, it was a reminder that exploration is not always sleek and pristine. Sometimes it is built from what is at hand, from hardware that has waited on shelves, from ideas that have been adapted and reshaped. When Magellan finally arrived at Venus, it slipped into an elongated or elliptical orbit. Instead of circling the planet in a neat, almost circular path, it swung in close on one side and farther out on the other, like a runner taking a long, looping track. During each close pass, the spacecraft aimed its radar instruments down through the clouds, sending pulses of radio waves toward the hidden surface. Those waves bounced off rock and slope and valley and then rose back up to be caught and recorded. At first, there were problems, software issues that had to be understood and worked around. Lines of code, written far away on Earth, had to be adjusted in light of how the spacecraft was actually behaving in the real, messy environment of space. But gradually, the system settled. Commands and responses flowed more smoothly. The radar began its steady work. Over time, pass after pass, Orbit after orbit, Magellan stitched together a new kind of picture of Venus. It wasn't a photograph in visible light, but a map built from reflections and timing, from the way radar echoes changed depending on whether they struck smooth plains, rough rocks, or the edges of steep slopes. These images became, and remain, the highest resolution views we have of the Venusian surface. What they showed was a world shaped in large part by fire. Low, broad volcanic domes appeared, features that looked, in radar, a little like blisters on the skin of the planet, gently raised and rounded. Long channels snaked across the landscape, carved not by water, but by ancient rivers of lava that had once flowed and cooled there. These channels sometimes ran for hundreds of kilometers, making it clear that molten rock had been able to move freely under Venus's heavy skies, finding paths downhill just as water does on Earth, but in a far hotter, more alien context. Something else stood out. On the Moon and Mars, the surfaces are pocked and battered by countless impact craters, the scars of billions of years of collisions with asteroids and comets. Venus, by contrast, showed relatively few. Its thick atmosphere acts like a shield, burning up or breaking apart most incoming space rocks before they can reach the ground intact. Only the largest and most energetic impacts manage to punch through the air and gouge holes in the rock below. As a result, the landscape in Magellan's images looked, in many places, strangely smooth and young, with far fewer ancient craters than one might expect on a planet that has existed for billions of years. There was another puzzle hidden in those radar patterns. Earth's outer shell is broken into plates that slowly drift, collide, and slide past one another over long spans of time. This process, plate tectonics, builds mountain ranges, opens ocean basins, and continually reshapes the continents. On Venus, in all that rich detail, clear signs of the same style of tectonic activity were not obvious. There were fractures and ridges, compressions and extensions, but not the neat, broad bands where one plate dives under another, or the long, clean scars of plate boundaries like those on Earth. It was as if the planet had chosen a different way to move and heat and release its inner energy. Once the main phase of radar mapping was complete, Magellan was asked to perform a different kind of listening. The spacecraft's orbit was adjusted so that it could measure very slight variations in its own motion as it flew over different regions of the planet. In places where the gravity was a little stronger, perhaps due to a buried mass of dense rock or a towering volcanic rise, the spacecraft would speed up almost imperceptibly as it passed. In regions where the gravity was a bit weaker, it would slow by a similarly tiny amount. By carefully tracking these changes from Earth, scientists could build up a map of Venus's gravitational field, a kind of invisible relief map that revealed how mass was arranged beneath the surface. On Venus, these localized changes in gravity were found to correspond closely to surface features, high standing plateaus, broad volcanic rises, and deep basins. The world's outer layers and inner structure seemed to be tied together in ways that were different from Earth, where oceans, mountains, and the movement of plates complicate the relationship between surface, shape, and gravity. From the mixture of radar images and gravity data, a new portrait of Venus emerged. It appeared that, perhaps about 500 million years ago, something dramatic had happened there, some large-scale event or long episode that had effectively resurfaced the planet. Vast areas looked as though they had been covered by relatively fresh lava flows, burying older terrain and leaving behind a comparatively young skin over an ancient body. The scarcity of very old impact craters fit this picture. If the surface had been largely melted and remade a few 100 million years ago, there would have been less time since then for new craters to accumulate. Yet, even though volcanoes and lava channels were common across the radar maps, Magellan could not clearly catch any in the act. It saw the traces of eruptions, the remnants of flows, the shapes of old domes and vents, but no direct signatures that said, unmistakably, "This volcano is erupting now." It was like walking into a room that smelled strongly of smoke and seeing charred wood and blackened walls, but never actually witnessing the fire itself. After Magellan's work, another watcher took up a different vantage point. In 2006, the European Space Agency's Venus Express mission slipped into orbit around the planet. While Magellan had focused its energy on looking through the clouds to the surface, Venus Express was designed to pay sustained attention to the atmosphere itself, to watch how it changed over years, how winds shifted, how heat moved, and how different gases rose and fell in abundance. For 8 years, Venus Express circled the planet, looping over the poles and passing again and again through the layers of the thick air. Its instruments measured the composition of the atmosphere in different altitudes and regions, particularly watching gases like sulfur dioxide, which on Earth is often associated with volcanic activity. At one point during the mission, the spacecraft registered a sharp rise in the amount of sulfur dioxide high in the atmosphere. There were at least 2 possible explanations. One was that the winds on Venus had changed, carrying sulfur dioxide from one region to another, lifting it or redistributing it in ways that made it seem more abundant in the places Venus Express was measuring. The other possibility was more exciting, that fresh sulfur dioxide had been injected into the atmosphere from below, carried upward by eruptions or ongoing volcanic processes. The spacecraft also watched in infrared, a kind of light that carries information about heat, from 3 particular locations on the surface regions known from Magellan's maps to be volcanic in nature. Venus Express saw increases in infrared radiation over time. These were gentle brightenings in the heat signature, not huge flashes, but they suggested that some spots on the planet were warming and cooling in a way that hinted at something active beneath. More small pieces of the puzzle followed. The infrared team saw short-term temperature changes in certain areas, fluctuations that rose and fell over just a few days. This kind of rapid change fit better with local events, possibly linked to volcanic or geothermal activity, than with slow, global shifts in weather. None of this was the simple, dramatic sight of lava fountains captured on camera, but together, these clues painted a picture that was hard to ignore. Venus, with its world-sized oven of a surface, might still be geologically alive, its volcanoes not just relics, but participants in the planet's present. As its fuel and systems aged, Venus Express was guided into a series of lower and lower passes that skimmed the upper layers of the atmosphere. In these final orbits, the spacecraft dipped into the planet's mesosphere, a region high above the main cloud deck like a fingertip, brushing the surface of a stream. The measurements it took there revealed unexpected ripples and waves in the thin air. Structures moving through the atmosphere that spoke of complex dynamics and energy, flowing even at altitudes where one might have expected stillness. In 2015, the mission came to an end. The spacecraft's path finally let the thickening atmosphere drag it down, and Venus claimed this watcher as it had claimed others before. Since then, there has been surprisingly little direct exploration of the planet. Proposals for new orbiters, new landers, even floating balloons and sample return schemes lie written in plans and studies, detailed and ambitious, waiting for the moment when they will be chosen and funded. For now, Venus remains a bright, steady light in our sky and a fiercely guarded secret beneath its clouds, a world we have touched only in fleeting, difficult ways, mapped in careful radar echoes and distant infrared glows, but not yet come to know as deeply as its nearness might suggest. It waits just next door, hot and heavy and restless, keeping most of its story to itself, while we gather the fragments we already have and quietly imagine the day will send new messengers into that thick, shimmering air. And yet, even in the years when no one is sending cameras down through its clouds or slipping new orbiters into place, Venus still plays a quiet role in many journeys. Spacecraft on their way elsewhere often curve in close to this bright neighbor, borrowing a little of its gravity to change course. From far away, it seems as though they are merely passing by, offering a brief glance and moving on. In the language of flight dynamics, though, they are doing something more subtle, letting the pull of a planet bend their paths, saving precious fuel and opening up voyages that might otherwise be too difficult or too costly to attempt. In 1974, this idea was still young. That year, NASA's Mariner 10 became the first spacecraft ever to use what we now call the gravitational slingshot effect on its way to another world. The target was Mercury, the small, dense planet tucked tight against the Sun. Getting there is not as simple as pointing and firing a rocket. The Sun sits in the middle, like a deep well of gravity, and as a spacecraft moves inward, it is pulled faster and faster, like a stone rolling downhill. If it arrives at Mercury going too quickly, it will simply race past, unable to slow down enough to stay. An Italian mathematician named Giuseppe Colombo studied that problem carefully and suggested a graceful solution. Instead of flying straight from Earth to Mercury, Mariner 10 would first swing by Venus. If the trajectory and timing were chosen just right, the probe could pass behind Venus in such a way that the planet's gravity would tug on it, reshaping its path and adjusting its speed. In that single, well-choreographed encounter, the spacecraft would not only save fuel, but it would also be set up to fly past Mercury not once, but several times. Its sun-centered orbit matching up with Mercury's position again and again. At the time, this was a daring piece of orbital choreography. Today, the same technique feels almost routine, used so often that it has become part of the quiet grammar of interplanetary travel. 10 days after launch, Mariner 10 needed only a modest course correction to stay on the intricate path Colombo had imagined. Controllers sent up instructions for a routine engine burn, the sort of small adjustment that nudges a spacecraft from a nearly right trajectory to a precisely right one. The burn itself seemed to go well. But when the time came for the craft to turn and reorient, something was off. Mariner 10 kept its bearings in space by looking for a familiar point of light, the bright star Canopus. A tracking sensor could lock onto that star and use it as a reference, a fixed point against which the spacecraft could measure its own orientation. But in the dark around the probe, tiny flakes of white paint had begun to drift away from its own body. One of those flakes wandered into the sensor's field of view and, for a moment, masqueraded as the star itself. Confused, the system believed it was pointed correctly when it was not. An automated backup procedure took over, scanning the sky and reacquiring the real Canopus. The crisis passed, but the underlying issue did not vanish. Flaking paint would continue to trouble the mission, a small, human-made snowstorm of debris that sometimes shimmered just enough to fool the spacecraft's eye. Even so, Mariner 10 pressed on, feeling the wide, slow pull of the sun as it moved toward its meeting with Venus. Traveling to the outer planets, a spacecraft fights against the sun's gravity, climbing slowly away from the center. Its motion is constantly being tugged backward, and small pushes can stretch that climb out into the distant dark. With the inner planets, the problem is reversed. The closer a craft gets to the sun, the more fiercely it is pulled forward, gaining speed as if sliding down a steepening slope. Mercury, hugging that gravitational well, is a difficult target to approach gently. Mariner 10's flyby of Venus acted like a hand on its back, not pushing, but redirecting, curving its path and trimming its speed so that it would meet Mercury at a sharper, more favorable angle. There was never enough fuel aboard Mariner 10 to slow down and settle into orbit around Mercury. That had not been the plan. Instead, its trajectory around the sun was chosen so that it would cross paths with Mercury 3 times, each encounter a brief, intense opportunity to look closely at the small planet. On the first pass, the spacecraft sent back pictures that revealed a world surprisingly familiar in some ways. A heavily cratered surface, scarred and pitted like our moon, with wide stretches of ancient terrain that had not been erased by air or water. Mercury is the smallest planet in the solar system, but it is also the most dense. Beneath its battered crust lies a large, iron-rich core that takes up a much greater fraction of its volume than Earth's core does for our planet. In Mariner 10's images, scientists noticed long, high cliffs, features called escarpments, cutting across the landscape. One of the most striking, named Discovery Rupes, slices through 2 craters and drops roughly 3 kilometers from top to bottom. These cliffs are thought to be the wrinkles of a cooling world. As Mercury's large core slowly lost heat over time, it would have shrunk slightly, pulling the outer layers inward and causing the crust to buckle and crack like the skin of a drying fruit. Mariner 10 did its work while carrying its own share of troubles. Its tape recorder, a mechanical heart that stored data when the spacecraft was out of direct communication with Earth, had a tendency to stick. The rates at which it could send information back were limited, forcing engineers to choose carefully which data to prioritize. Attitude control was another persistent worry. With some of the normal ways of adjusting its pointing compromised, the team learned to use something gentler and more subtle: the pressure of sunlight itself. Photons streaming from the sun exerted a tiny but continuous push on the probe's high-gain antenna and solar panels. By adjusting their orientations, controllers could use this faint pressure as a kind of light touch steering, helping to keep the spacecraft's instruments pointed where they needed to be. Despite all of this, the mission's rhythm continued. With each return to Mercury, Mariner 10 added new slivers of the planet to its portrait. However, because of the way its path and Mercury's rotation lined up, the same side of the planet faced the sun, and therefore faced the spacecraft during each pass. In the end, only about 45% of Mercury's surface was seen and mapped. The rest would remain hidden in darkness and uncertainty for decades. From its instruments, Mariner 10 also discovered that Mercury possesses a very thin atmosphere, or exosphere, made up primarily of helium and a few other light particles. It was not an atmosphere in the sense we're used to on Earth, no thick blanket of air to breathe or to push against the ground, just a faint, tenuous collection of atoms hovering above the surface, easily stripped away and replenished by various processes. Several months after its third and final close flyby of Mercury, Mariner 10 exhausted its small supply of fuel. Without the ability to adjust its course any further, it could no longer meaningfully aim or control its instruments. The mission was declared over, but the spacecraft itself did not stop. It remains in its orbit around the Sun, a silent object circling through the inner solar system, crossing paths with Mercury's orbit again and again, unseen and unheard, like a message that has already been read and gently folded away. It would be more than 30 years before another spacecraft returned to Mercury. In 2004, NASA launched a mission with a more ambitious goal, not just to fly past, but to go into orbit and stay. The spacecraft was called MESSENGER, short for Mercury surface, space environment, geochemistry, and ranging. And it had to face the same fundamental challenge: how to live so close to the Sun without being overwhelmed. MESSENGER's body wore a large woven ceramic sunshield, like a rigid, heat-resistant curtain, always meant to face the Sun and keep the rest of the spacecraft in its shadow. Behind that shield, instruments and electronics could remain at temperatures they were designed to endure. Instead of a traditional dish antenna, MESSENGER relied on a phased array system that could be electronically steered, allowing the spacecraft to talk to Earth without having to twist and risk exposing its more vulnerable parts to direct sunlight. After a year in space, MESSENGER returned not to Mercury, but to Earth itself, sweeping past for a gravity assist that adjusted its orbit around the Sunday. Even though it was not a large spacecraft, it carried a relatively powerful engine, needed for the many course corrections and the eventual, demanding burn required to ease into orbit around Mercury rather than just shoot past from Earth. It continued on to Venus, passing the cloud-wrapped planet twice. Each flyby allowed it to shed some of the speed it had gained while falling inward toward the Sun, like a traveler using familiar landmarks to slow down before reaching a final destination. 3.5 years after launch, MESSENGER made its first close approach to Mercury, but that encounter was only another step in a longer path. The probe would swing by the small planet twice more, refining its trajectory, gathering early data, and gradually setting up the geometry needed for orbit insertion. All told, nearly 7 years passed between the moment the spacecraft left Earth and the day it finally fired its engine at just the right place and time to let Mercury's gravity catch it. Throughout the mission, the engineering team carried one more constant concern: the orientation of that sunshield. No matter what scientific observations were being made, no matter which way the instruments wanted to look, the shield had to remain roughly between the spacecraft and the Sunday. It was like trying to explore a landscape while always keeping a broad hat tilted just so, never letting the light strike your face directly. Within that constraint, MESSENGER turned, measured, mapped, and listened, learning the details of a world that Mariner 10 had only half revealed. And in the background of those careful maneuvers, Venus remained part of the story, not as the main character this time, but as a quiet helper. Its gravity, felt but never seen, had reached out to reshape MESSENGER's path, just as it had once bent the flight of Mariner 10. In that way, the bright planet between us and the Sun continues to act as both destination and doorway, a place of its own fierce mysteries and a stepping stone that helps us reach others. Thanks to those gentle tugs from Venus, MESSENGER finally arrived where it had been headed all along. Being in orbit gave it something Mariner 10 had never had: time. Instead of rushing past Mercury in a single long blink, it could circle again and again, letting the small planet slowly turn beneath it. With each pass, new ground came into view, and the blank spaces in the old maps began to fill. The patchwork half-globe that Mariner 10 had offered decades earlier gradually grew into a nearly complete portrait. Among all the features that emerged, one dominated the story of Mercury's surface: the Caloris Basin. It is an ancient impact scar, more than 1,500 kilometers across, so wide that if you could stand at one end, you would not be able to see its far rim through the curve of the planet. Mariner 10 had glimpsed part of this basin in dawn light, sailing over a region sprinkled with strange, radial patterns. But much of it had been hidden in shadow, on the hemisphere that was turned away during those fleeting encounters. To finally see the whole structure was like stepping back from a painting that had always been viewed too close. The shapes suddenly made sense. Messenger's orbit also allowed a different kind of map to be drawn, one not of colors or textures, but of light and darkness. Near Mercury's poles, the spacecraft traced out where sunlight could reach and where it could not. Because Mercury's rotation axis is barely tilted, unlike Earth's, it does not experience strong seasons. The sun always hovers at roughly the same height in the sky over any given latitude. That means that in deep craters near the poles, sunlight never climbs high enough to shine onto the floors. Their rims cast permanent shadows, shielding the bottom from direct light for millions, perhaps billions, of years. In maps of the southern polar region, this was turned into color. Bright shades for places that bask in frequent illumination, darker tones for regions that see only glancing rays, and the deepest hues for those eternally shadowed pockets. It was in those cold, hidden hollows that Messenger found something unexpected for a world so close to the sun: substantial deposits of water ice. Radar and neutron measurements pointed to materials that reflected and absorbed in just the ways ice does, lying like buried frost in the darkness. On the sunlit side of Mercury, the ground can grow hot enough to melt metal, but in those shadowed craters at the poles, temperatures remain low enough for ice to survive. Protected from direct heating by geometry alone, it is a quiet reminder that even a scorched world can harbor cold secrets if the angles line up just right. As Messenger continued its work, its life was extended more than once. Each mission extension was like being granted a few more evenings with an old storyteller, knowing that the voice would not last forever, but grateful for every additional tale. The spacecraft's fuel, however, was finite. Tiny bursts from its thrusters were needed to keep its orbit from slowly decaying, and eventually, there was simply nothing left to burn. In 2015, after years of circling and sending back data, Messenger's path dipped lower and lower until Mercury's gravity pulled it into the surface. The probe ended its life in the very landscape it had spent so long mapping, becoming one more small, unseen mark on a world now far better known. Even before Messenger's final descent, plans were already in motion for another visitor. A new mission, Bepi Colombo, named in honor of Giuseppe Colombo, the mathematician who had first worked out the elegant multi-flyby path for Mariner 10, was on its way. Unlike the earlier, single-nation missions, Bepi Colombo is a joint effort between JAXA, the Japanese Space Agency, and the European Space Agency. It carries multiple spacecraft and instruments, each with its own set of questions about Mercury's surface, interior, magnetic field, and environment. The journey is a long, looping one. It will take about 7 years for Bepi Colombo to spiral inward, using repeated flybys of Earth, Venus, and Mercury itself to gradually adjust its orbit around the Sun and shed the excess speed that comes with falling toward the star. Only after all those careful gravitational exchanges will it finally be able to settle into orbit around the smallest planet, continuing the work that Messenger began answering questions that only appeared once the first set of answers had been gathered. While one part of human curiosity has been drawn inward toward the sun and its nearest companions, another part has always been pulled outward toward the wide, cold frontier where the outer planets circle in their slow, dim arcs. Out there, two of the most elusive worlds, Uranus and Neptune, have been visited up close only once, by a single spacecraft moving steadily away from home. Voyager 2, launched in 1977, along with its twin, Voyager 1, carried this particular burden of exploration. The timing of its departure allowed it to take advantage of a rare alignment of the four giant outer planets, Jupiter, Saturn, Uranus, and Neptune. In that special configuration, gravity assists could be choreographed so that a single spacecraft, with just a limited supply of fuel, could make close approaches to each of them in turn. It was like finding a path of stepping stones across a vast river, each stone positioned just right to let you reach the next. In 1986, after years of travel, Voyager 2 approached Uranus. From Earth, Uranus is a pale, distant dot, its details smoothed out by the enormous distance. Up close, Voyager found a world that had lived through a dramatic past. Long ago, Uranus is thought to have been struck by a massive object, a collision so powerful that it knocked the planet's axis over. Instead of spinning like a top with its poles pointing roughly up and down relative to its orbit, Uranus rolls more like a ball on its side. Because of that tilt, about 90 degrees from what we would consider upright, the planet's seasons are extreme and strange. For roughly half of its long year, one hemisphere faces the sun almost continuously, bathing in unending daylight, while the opposite side sits in long, deep night. Then, slowly, over decades, the roles reverse. In a way, Uranus has an east and west pole more than a north and south in the familiar sense. The rings that circle Uranus follow its equator, which means they are oriented in a north-south direction as seen from much of the solar system. Voyager 2's instruments revealed that these rings, faint and narrow, encircle the planet like thin, dark bands. The spacecraft also discovered 11 new moons, small, irregular companions that had been too dim and too close to the planet's glare to be seen from Earth before. Measurements showed that Uranus's magnetic field is oddly misaligned, both tilted relative to its rotation axis and offset from the planet's center, adding another layer of strangeness to an already unusual world. In visible light, the images Voyager 2 returned of Uranus looked almost disappointingly plain, a smooth, bluish-green sphere with little obvious structure. At the time, it seemed to be a bland, featureless planet, especially in comparison with the storm bands of Jupiter or the dramatic rings and cloud patterns of Saturn. Only later, with observations from the Hubble Space Telescope and other instruments, did we learn that Uranus can show more active weather at different points in its long seasonal cycle, with bright clouds and atmospheric features appearing when the lighting and internal dynamics line up just so. Voyager happened to visit at a quieter, more subdued moment, catching the planet in a kind of atmospheric repose. Among Uranus's moons, one in particular captured scientists' attention, Miranda, the largest of the small inner moons. Voyager 2's close images showed a surface so chaotic and varied that at first glance, it looked almost stitched together from mismatched pieces. There were regions of deep canyons, others of strangely smooth plains, and vast, patchwork-like patterns where blocks of crust seemed to have shifted and tilted. The jumbled terrain was so dramatic that some researchers initially speculated Miranda might have been shattered by a tremendous impact in the distant past and then reassembled from its own fragments, leaving scars and mismatches behind. Over time, another explanation rose to prominence. The complex patterns on Miranda's surface might instead be the result of intense tectonic activity driven by the gravitational pull of Uranus. As the moon moved in its orbit, tiny but persistent flexing from tidal forces could have heated its interior, causing parts of the crust to crack, rise, and fall in elaborate ways. Rather than a broken object glued back together, Miranda might be a world that has been kneaded and reshaped from within, its face bearing the marks of that restless history. As Voyager 2 sped away from Uranus, a new perspective revealed still more details. With the sun behind the planet, its light streaming through the rings from the far side, two additional faint rings became visible, encircling Uranus in delicate, backlit arcs. It was as if, in the moment of farewell, the planet had turned slightly to show the spacecraft one last, subtle secret. From there, Voyager 2 headed toward Neptune, the last of the classical planets, and, at that time, the outermost recognized planet in the solar system. The journey from Uranus to Neptune would take about 3 years. During that long coast, engineers on the ground prepared for a set of unique challenges. Neptune lies roughly 30 times farther from the Sun than Earth does, so the sunlight there is only about 1,000th as bright. For photography, that means long exposures are needed to gather enough light to make clear images. But Voyager 2 was not drifting slowly. It was hurtling through space at high speed. If the spacecraft simply stared at Neptune during a long exposure, the motion would smear the images, turning points of detail into streaks. To avoid this, engineers carefully calculated how quickly Voyager would have to swivel, just so, while the camera's shutter was open, turning the spacecraft in such a way that the movement canceled out the apparent motion of the planet in the frame. It was like trying to take a sharp photograph from the window of a fast-moving car by panning the camera precisely to keep one distant tree steady in view. In June 1989, the first distant images of Neptune began to arrive. On screens in control rooms and, eventually, in newspapers and on television sets around the world, a small blue disk slowly grew clearer and more detailed as Voyager approached. Even before the final close passes, people sensed that the data streaming back from this aging spacecraft was still reshaping our understanding of the solar system's edges, turning what had once been mere points of light into real places, with weather, moons, and stories of their own. All of this happened in a world before instant sharing and live feeds, before the habit of checking a screen in your hand for updates. The images and discoveries traveled more slowly then, carried by broadcasts and printed pages, but the quiet wonder they stirred was much the same. A feeling that, even from our small, bright world, we had managed to reach out and gently touch the farthest, coldest planets circling in the dark. At the Jet Propulsion Laboratory, people gathered close around old televisions and monitor screens, shoulders almost touching, eyes fixed on images that didn't appear all at once, but crept in line by line. Each new strip of picture from Voyager 2 slid into view slowly, building Neptune's face like a curtain being drawn up from the bottom. There was no instant replay, no scrolling feed, just the quiet patience of watching a distant world reveal itself in thin, pale bands of light. Compared with Uranus, Neptune seemed, in some ways, more familiar. Its axis is tilted by about 30 degrees, not so different from Earth's, and it spins in the same direction we do. It is slightly more massive than Uranus, yet its diameter is a little smaller, as if the planet had been pulled inward, packed more tightly. And even though Neptune orbits farther from the Sun than its fellow ice giant, it glows with more warmth from within. Somewhere deep below its blue clouds, an internal heat source is at work, feeding energy into the atmosphere and stirring it into motion. That hidden heat drives wild weather. Voyager 2 measured winds racing around Neptune at more than 2,000 kilometers an hour, the fastest winds known in the solar system. In the upper atmosphere, thin cirrus clouds traced those currents, delicate streaks of ice crystals swept along by invisible jets. On the disk of the planet itself, the spacecraft recorded a great dark spot, a storm system in the southern hemisphere. Like Jupiter's great red spot, it was an anticyclone, a vast, swirling high-pressure system as large across as Earth in its entirety, slowly rolling across the blue. For a little while, that dark storm became part of how we pictured Neptune, a calm-looking planet with a single, brooding eye. But when the Hubble Space Telescope looked years later, in 1994, the spot was gone. The giant storm had faded, broken apart, or sunk beneath the visible clouds. In its place, in the northern hemisphere, a new dark spot began to form. On this distant, cold world, even the largest storms are temporary, rising and fading over years, reminding us that the deep outer planets are not frozen statues, but living, changing spheres of gas and ice. Voyager 2's final close look at a major body in the solar system was not of Neptune itself, but of its largest moon, Triton. Triton orbits Neptune in the wrong direction, moving backward relative to the planet's rotation. This retrograde path stands out because nearly all other large moons circle their planets in the same direction their host spins. Triton's backward orbit is a clue. It likely did not form in place alongside Neptune, but was captured long ago, drawn in from elsewhere, perhaps from the Kuiper Belt, a band of icy worlds beyond Neptune's path. That capture would have been a violent, complicated dance, reshaping Triton's orbit and possibly its interior too. Voyager's cameras showed a strange, cold surface etched with ridges, planes, and dark streaks. It was a fitting last close-up, a moon that did not quite belong where it was, circling a planet at the edge of our familiar system. Beyond Neptune, there were no more planets to visit. Voyagers 1 and 2 had done their grand tour. To save power and extend their lives, the cameras aboard Voyager 2 were shut down. It would no longer send back pictures, but both spacecraft continued outward, measuring the faint, fading influence of the solar wind, the stream of charged particles flowing from the sun, and the boundary where that wind meets the thin gas between the stars. They became, in a way, weather stations on the frontier of the solar system, drifting slowly into interstellar space. To this day, that single passage by Voyager 2 remains our only close encounter with the ice giants. No other mission has flown past Uranus or Neptune up close. Those brief visits, captured on flickering screens decades ago, still anchor much of what we know about those worlds. On the 19th of January, 2006, another spacecraft left Earth on a different kind of journey outward. An Atlas V rocket rose into the sky, its engines thundering, carrying a payload that seemed almost small compared with the power beneath it. The spacecraft was New Horizons, and from the moment it left Earth's gravity well, it was moving faster than any interplanetary probe before it. Its destination lay beyond the orbits of Neptune and the known giants. The Kuiper Belt, the wide ring of icy bodies at the edge of the solar system. Its first goal in that distant region was a world that had long been counted as the 9th planet, Pluto. A little more than a year after launch, New Horizons reached Jupiter. There, the giant planet played the same quiet role it had played for Voyager and others before. A source of gravity to bend and boost the spacecraft's path. By flying past Jupiter at just the right angle and time, New Horizons received a gravitational assist that cut about 3 years from its flight time to Pluto. In exchange for that invisible nudge, it also took the opportunity to look briefly at Jupiter and its surroundings, gathering bonus science on the way. After it left Jupiter behind, the spacecraft settled into a different rhythm. There were no more planets to pass for a long while, only the slow widening of the sun's circle behind it and the thinning of the solar wind ahead. To conserve power and reduce wear, New Horizons entered a kind of hibernation. Most of its systems were powered down, leaving just enough awake to keep time, maintain orientation, and send a simple weekly message back to Earth. A small, steady, all is well signal crossing hundreds of millions, then billions of kilometers. It took more than 9 years for New Horizons to reach Pluto. In that long interval, our understanding of Pluto's place in the solar system shifted. As astronomers discovered more and more objects of similar size out in the Kuiper Belt, it became clear that Pluto was not alone in its category. To keep the word planet meaningful, the astronomical community eventually agreed on a new definition. A planet had to orbit the Sun, be massive enough to pull itself into a nearly round shape, and clear its orbit of other debris. Pluto passed the first 2 tests, but not the third. It shared its orbital zone with other bodies. Under the new definition, it was reclassified as a dwarf planet. The change in label did not make Pluto any less real or any less interesting. If anything, it framed the New Horizons mission in a softer light. The spacecraft was on its way to a representative of a whole population of small, icy worlds. A first close look at the kind of object that might be common in the outer solar system. When New Horizons finally arrived in 2015, Pluto did something quietly astonishing. It turned out to be active, varied, and beautiful. The images showed a surface marked by broad, bright plains and dark, ancient regions, by sharp mountains and smooth basins. Some of the mountains rose as tall as major earthly ranges, but they were not made of rock. In Pluto's distant cold, water ice is as hard as stone, and the peaks are built from that frozen water, laced in places with ices of methane and other gases. The bright, heart-shaped plain of Sputnik Planitia hinted at ongoing reshaping. Patterns on its surface suggested convection, slow overturning of nitrogen ice, like thick, cold batter being stirred over geologic time. The absence of many impact craters in some regions suggested that parts of Pluto's face are young, resurfaced by processes still at work. In that bitter cold, tectonic forces seemed to be sculpting the landscape, but with ices instead of molten rock. Above the surface, New Horizons detected a thin atmosphere, made mainly of nitrogen, extending higher than many had expected. As Pluto moves closer to and farther from the Sun along its stretched-out orbit, some of the surface ices can sublimate into gas and then refreeze, breathing the atmosphere in and out over long seasons. After sweeping past Pluto, New Horizons continued on over Charon, its largest moon. Charon is about half the size of Pluto, and together the 2 bodies form a kind of double system, each circling a point in space between them, rather than one cleanly orbiting the other. Charon's surface is carved by deep canyons and marked by contrasting zones of brighter and darker terrain. Some evidence hints at the possibility of ice volcanoes, places where slurries of water and other ices may once have welled up from below and flowed across the surface before freezing solid. Because Pluto and Charon are tidally locked to one another, always showing the same face to each other, someone standing on Pluto would see Charon hanging in the same place in the sky, never rising or setting, only slowly changing phase. It would be a constant companion, a large, pale disk looking back across the narrow gulf of space between them. Once its fast flyby was over, New Horizons did what many spacecraft do after intense encounters. It turned inward, in a sense, and began the slow work of sharing what it had seen. All the data it had recorded during those precious hours needed to be sent home, but distances that large stretch even light itself. From the region of Pluto's orbit, it takes about 4.5 hours for a radio signal, traveling at the speed of light, to reach Earth. The data link was gentle, only about 1 kilobit per second, far slower than the connections many people use in their homes. Bits of information flowed steadily but sparsely across the dark, like snowflakes drifting through a wide, empty field. It took 469 days, well over a year, for all of the Pluto and Charon data stored aboard New Horizons to be fully transmitted to Earth. Somewhere in that long stream of bits were the details of mountains made of ice, plains of frozen nitrogen, hazy layers of atmosphere, and the colors and textures of a world no one had ever seen clearly before. The spacecraft itself kept going, its path carrying it deeper into the Kuiper Belt, while its memories arrived at Earth slowly, patiently, and were turned back into images and measurements, into a story of a small, distant world that turned out to be far more alive in its own frozen way than anyone truly expected. Far beyond the orbits of the known planets, where the sun is only a small, sharp light in a black sky, New Horizons kept going. Early in 2019, long after its brief, dazzling visit to Pluto and Charon, the spacecraft slipped past another distant body, a small trans-Neptunian object nicknamed Ultima Thule, a contact binary shaped a little like two snowballs gently pressed together. Out there in the Kuiper Belt, where countless icy remnants from the early solar system drift in slow, cold paths, New Horizons brushed by this quiet relic and then continued on, its mission extended, its instruments still listening to the thin, lonely environment at the edge of the sun's reach. All of these journeys past Jupiter's storms, Saturn's rings, Pluto's icy plains, and the dim Kuiper Belt are lit by the same star. Our sun is one among billions, but to us, it is everything. A giant nuclear furnace at the center of our planetary family, patiently fusing hydrogen into helium, flooding the solar system with light and warmth. Every leaf that has ever opened, every breath of air on Earth, every drop of liquid water owes its existence to that steady output of energy. Yet being so close to a star is a mixed gift. We need the sun's light to live, but we are also bathed in radiation and streams of charged particles that could easily strip away our atmosphere and batter the surface with harmful energy. What lets life flourish here is not just the sun's generosity, but Earth's own protection, a magnetic field that wraps around the planet like an invisible shield, and an atmosphere thick enough to soften and scatter the harsher parts of the solar storm. The sun is not a calm lamp. Its surface seethes and knots, threaded with loops of magnetic fields that twist, snap, and reconnect. Regularly, It hurls great clouds of charged gas into space bursts called coronal mass ejections. When one of those eruptions happens to be aimed our way and reaches Earth, it can disturb the magnetic field and upper atmosphere so strongly that systems we've built, power grids, communication networks, satellites feel the impact. Transformers can overload, radio signals can falter. The space around Earth can become a rougher sea for any spacecraft crossing it. In 1859, long before satellites and global power lines, the Sun offered a dramatic lesson in how far its influence could reach. That September, an English astronomer named Richard Carrington was in his observatory, quietly sketching sunspots on the solar disk as he did on many days. As he watched, an intensely bright patch flared to life near one of the spots, so sudden and vivid that it stood out even against the glare of the sun itself. It lasted only a short time, but it was unlike anything he had seen. Less than 18 hours later, people around the world began to notice the sky. Auroras, those shimmering curtains of colored light usually confined to high latitudes, spread far from their usual haunts. In places where such displays were almost never seen, the night glowed with moving bands and patches of green and red. In North America and Europe, telegraph operators found their systems behaving strangely. Lines sparked. Equipment hummed and clicked of its own accord. Some workers reported receiving electric shocks when they tried to adjust the instruments. In some cases, the charged currents induced in the long wires were strong enough that messages could still be sent even with the power supplies disconnected. For the first time, people began to draw a direct line between violent events on the sun and disturbances here on Earth, between a bright flash on a distant star and the quivering of compass needles, the flicker of auroras, the misbehavior of telegraph lines. The storm came to be known as the Carrington event, and it hinted that our planet lives not in isolation, but inside a changing bubble of solar influence. Even before that, observers had been quietly tracking the sun's moods. Since the 1700s, careful records of sunspots, those darker, cooler patches on the sun's surface, had shown a pattern. The number of spots rises and falls in a cycle lasting about 11 years. At some times, the sun is more blotched and active, at others more smooth and subdued. But the deeper workings behind those changes and the way they connected to space around Earth would not start to come into focus until the age of satellites. In 1958, the United States launched its first successful satellite, Explorer 1. James Van Allen was the chief scientist for the mission, and the small spacecraft carried, among other instruments, a detector for high-energy particles, cosmic rays, and other charged visitors from space. The launch placed Explorer 1 into an orbit that was more elongated than planned, stretching much farther from Earth at its farthest point than expected. As the satellite climbed and dipped along that path, the readings from the particle detector changed in ways that were hard to ignore. At certain altitudes, the detector registered far fewer counts than one would expect, as if it were passing through a region where radiation was being blocked or absorbed. At others, the counts jumped dramatically. Piecing together these variations, Van Allen and his colleagues realized that the Earth is surrounded by bands of trapped charged particles, regions where electrons and ions from the sun are caught and guided by the planet's magnetic field, spiraling along invisible lines that loop from pole to pole. These zones became known as the Van Allen belts. The discovery had far-reaching implications. Those belts are not smooth or static. They swell and shrink, intensify and soften with changes in solar activity. The energetic particles within them, pose a real risk to spacecraft and astronauts. Any mission that passes through must be designed with that hazard in mind, with trajectories chosen and shielding arranged so that sensitive electronics and human bodies are not exposed for too long. Around the same time, another piece of the puzzle was being worked out on paper. In 1957, physicist Eugene Parker, working at the University of Chicago, suggested that the sun doesn't just occasionally throw off bursts of material. It is constantly shedding a stream of charged particles in all directions, flowing outward through the solar system. He called this continuous outflow the solar wind. The idea was bold. Many in the astronomical community at first found it hard to accept. A steady, supersonic wind of plasma filling the space between planets seemed almost too dramatic. But soon the first Russian and American spacecraft began sending back evidence that vindicated Parker's theory. Wherever they went, they encountered a background flux of charged particles streaming outward from the sun, varying in strength and speed, but always present. The solar wind turned out to be the missing explanation for several phenomena that had long been observed but not fully understood. One of the most visual is the behavior of comet tails. No matter where a comet is in its orbit, its tail always points away from the sun, not along its direction of travel. Under the influence of the solar wind and sunlight, dust and gas released from the comet are pushed outward, forming tails that are shaped and combed by the flow of particles from the sun, like smoke in a moving breeze. Parker's model of a supersonic solar wind plasma, flowing faster than the speed at which disturbances can travel through it, described a dynamic environment, one where gusts and rarefactions ripple through the solar system. Earth sits inside that flow, and our magnetic field carves out a protective cavity within it, diverting most of the wind around us. In doing so, it helps preserve the atmosphere. Without a strong global magnetic field, the continual battering by the solar wind could, over long stretches of time, strip away air and water, as is thought to have happened on Mars. To watch the sun more closely and understand the wind and storms it sends, a dedicated sentry was placed in a special part of space. In 1995, the Solar and Heliospheric Observatory SOHO was launched. Instead of orbiting Earth directly, SOHO was guided to a point between Earth and the Sun, where the gravitational pulls of both balance in a useful way. At this location, known as the first Lagrange point, or L1, a spacecraft can remain in a relatively stable position, always keeping the Sun in view without constantly circling the Earth. From this quiet perch, about 1.5 million kilometers sunward of our planet, SOHO watches. One of its key instruments, called LASCO, uses a coronagraph, a disk that blocks out the bright face of the Sun so that the faint outer atmosphere, the corona, can be seen. In LASCO's images, the central glare is hidden and the delicate wisps and loops of the corona spread outward, revealing the structure of the Sun's magnetic field as it arches into space. When a coronal mass ejection occurs, LASCO can see the billowing cloud of plasma expanding away, helping scientists estimate its speed and direction and giving us early warning of storms that might be headed toward Earth. The planets themselves appear in these images too, as bright points slowly moving across the field of view. Because they are so bright compared with the background, their light can overwhelm the camera's sensor, creating horizontal streaks or lines, flanking them, artifacts of the instrument, reacting to the intensity, like after images in an eye that has looked at something dazzling. Another instrument on SOHO, the Extreme Ultraviolet Imaging Telescope, looks at the Sun in wavelengths of light that human eyes cannot see. In that part of the spectrum, the solar surface and corona appear structured and intricate, threaded with loops and arcs of hot plasma. The telescope has captured waves rippling out from solar flares, disturbances moving across the solar surface and spreading into the corona. When especially energetic particles from these events rush past the spacecraft, they can strike the camera's detector directly, showing up as a sudden sprinkling of bright specks across the image, like static or snow on an old television screen. Taken together, these measurements turn the sun from a featureless globe into a living, flickering presence, its moods recorded in frequencies and flashes. While New Horizons drifts on through the deep outer dark, sampling the quiet edge of the solar wind, observatories like SOHO keep a steady eye on the source, watching the great furnace at the center of it all as it flares, rests, and breathes charged particles into the space where all our journeys unfold. High-energy sunlight, especially in the extreme ultraviolet, never really holds still. It flickers and shifts from minute to minute, and it swells and fades over the sun's roughly 11-year activity cycle. To us at the surface, these changes are softened by distance and filtered by air, but high above, in the thin reaches of the atmosphere, they matter a great deal. When the sun grows more active, more of that intense radiation pours into Earth's upper layers of air. It heats and stirs them, raising tides not in the oceans, but in the atmosphere itself. These tides grow stronger with altitude, swelling the outermost layers so that they puff outward a little, like the surface of a lake ruffled by wind. Low-orbiting satellites, which normally skim through very thin air, suddenly find that the medium around them has grown thicker. The drag increases. Their orbits begin to shrink faster than planned, and engineers must spend precious fuel to lift them back up. Communication systems feel these moods too. Signals that rely on the delicate structure of the ionosphere can be bent, delayed, or disrupted. GPS services, which depend on timing and clean paths through the upper atmosphere, may wander or degrade when the sun is particularly restless. All of this makes it important to keep a constant, careful eye on the star that lights our days. In 2010, NASA placed a new watcher in orbit, the Solar Dynamics Observatory, or SDO. Instead of circling the Earth in a low, fast path, SDO was given a geosynchronous orbit with an inclination of about 28 degrees. That means that from our point of view on the ground, it lingers over the same region of the planet, keeping an almost unbroken view of the Sunday. Day after day, year after year, SDO stares at our star, recording its subtle changes in exquisite detail. The observatory looks at the sun in many different wavelengths of light, each tuned to a particular temperature range or layer of the solar atmosphere. Some channels highlight the relatively cool surface. Others pick up the hotter chromosphere, the even hotter transition region, or the million-degree corona. By switching between these views, or looking at them side by side, scientists can trace how activity in one layer ripples into another, how a flare that brightens one band of light twists, loops, and arcs somewhere else. Part of what makes the sun so complex is that it is not a solid body. There is no rigid surface that turns as one. Instead, the sun is made of plasma matter so hot that atoms have been stripped into loose electrons and ions. In this state, the gas becomes an excellent conductor of electricity, and it responds strongly to magnetic fields. The sun does not simply rotate, it swirls and shears. At the equator, it completes a turn in about 25 days. Near the poles, it takes closer to 38. Different latitudes spin at different rates, and that differential motion stretches and twists the sun's magnetic field lines into an ever more tangled web. The layer we see with our eyes, the photosphere, glows at a temperature of around 6,000 Kelvin. In visible light, it looks granulated, like a field of tiny, bright cells, each one the top of a convective plume of hot gas, rising, cooling, and sinking again. Against that bright backdrop, sunspots stand out as darker patches. They are not truly cold, only cooler than their surroundings, but they mark places where concentrated magnetic flux has pushed aside and impeded the boiling motion below, throttling the heat flow to the surface. Many are as large as Earth, or larger dark islands in a sea of fire. If you look beyond the visible spectrum at those same regions, another layer of structure appears. Arched loops of glowing plasma rise above the spots, tracing the magnetic field lines that leap from one polarity to another. These loops can stretch tens of thousands of kilometers into the low solar atmosphere, shaping the motion of gas like invisible rails. Just above the photosphere lies the chromosphere, a thinner, more delicate layer where gravity begins to lose its tight hold and dynamic thermal and magnetic forces take over. In the chromosphere, temperatures climb to around 8,000 Kelvin. Here, spicules, thin jets of plasma shoot upward, and bright ribbons flicker along active regions. It is a place where the sun's churning interior starts to give way to the more tenuous, electrically charged outer envelope. Higher still is a narrow, intricate band called the transition region. Across this relatively small height range, temperatures leap from thousands of degrees to hundreds of thousands. In this zone, the gas becomes increasingly ionized and responsive to the changing magnetic field, and the energy transport mechanisms shift. Temperatures in the transition region can exceed 500,000 Kelvin, even though it lies above layers that are much cooler. Above that, spreading far out into space, is the corona, the sun's extended atmosphere. During a total solar eclipse, when the moon briefly covers the bright disk, the corona appears as a pale, ghostly halo of streamers and plumes, reaching outward in soft, feathery shapes. In images from X-ray and extreme ultraviolet telescopes, it looks more like a nest of luminous threads and arches. Temperatures here can reach 1,000,000 Kelvin or more, far hotter than the photosphere below. This strange inversion, where the air above the surface is hotter than the surface itself, has puzzled scientists for decades. One might expect things to cool with height, as they do in many familiar settings. Instead, the sun's atmosphere heats up again once you move beyond the visible layer. Various ideas have been put forward: waves dumping their energy, tangled magnetic fields, snapping and reconnecting in countless small events, but no single explanation has yet tied everything together. The corona remains a place where our understanding thins, even as our images grow sharper. Within this fiery atmosphere, space weather is born. Solar flares erupt as sudden brightenings, releasing bursts of electromagnetic radiation that span from low-energy radio waves to high-energy X-rays and gamma rays. On our sun, these flares can be powerful enough to disturb communications and create bursts of particles that race outward. Seen from far away in the right wavelengths, they appear as sharp, brilliant flashes on the solar limb or in active regions, lasting minutes to hours. Other stars, especially younger or smaller ones, can be even more volatile. Red dwarf stars with masses and sizes significantly smaller than the sun's often have strong magnetic fields and can produce flares that dwarf anything we have observed on our own star. In April 2014, NASA's Swift Gamma Ray Observatory, designed to rapidly pinpoint brief bursts of gamma rays and X-rays, detected an extraordinary event from a nearby red dwarf known as DGCVN. The initial blast from that star was about 10,000 times stronger than the largest solar flare ever recorded from our Sunday, and it was not a single outburst. Over the course of 2 weeks, Swift saw 7 major flares erupt from DGCVN, one after another. The star is roughly 1/3 the Sun's size, but it spins about twice as fast. That rapid rotation helps drive a much more intense dynamo in its interior, building magnetic fields that are stronger and more twisted. The prevailing view is that the strength and complexity of a star's magnetic field are closely tied to the intensity of the flares it can produce. On a world orbiting such a star at the right distance for liquid water, these storms could be frequent, dramatic, and perhaps harsh for any fragile atmosphere. Back at our own sun, another kind of outburst plays a different role. Coronal mass ejections are not just flashes of light. They are vast clouds of plasma, billions of tons of charged particles hurled outward from the corona. These clouds ride along with the solar wind, expanding and traveling through interplanetary space at hundreds to thousands of kilometers per second. If one intersects Earth's orbit at the right time, it can compress our magnetic field, drive strong currents in the upper atmosphere, and paint the polar skies with brilliant auroras. Although coronal mass ejections are often seen near flares and active regions, the exact relationship between flares and CMEs is complicated. Some flares occur without a major ejection. Some ejections happen with only modest flaring. The two phenomena clearly share roots in the Sun's magnetic unrest, but the precise ways in which they trigger each other or don't remain an active area of study. They are different expressions of the same deep agitation, like lightning and thunder, that do not always arrive together in the way we expect. By watching the Sun in many wavelengths at once, observatories like SDO and others have been able to measure temperatures and motions with high precision. The more we look, the clearer the dramatic rise in temperature above the photosphere becomes, and the more insistent the coronal heating mystery feels. We can map loops and waves, track flares and ejections, and model the flow of plasma, but a fully satisfying, simple explanation still stays just out of reach. For now, we live with a kind of informed humility. We understand that our star is a boiling, magnetic, constantly changing sphere of plasma. We can predict some of its moods, brace for some of its outbursts, and admire the patterns it weaves in ultraviolet and X-rays. And at the same time, we accept that even this star we depend on every day still keeps some of its deepest workings veiled, asking us, gently but firmly, to keep watching and listening a little longer. In 1990, while much of the world went about its ordinary days under a familiar blue sky, a shuttle rose on a pillar of flame. Discovery lifted off, carrying with it a small, quiet traveler with a very particular destination in mind. The spacecraft was called Ulysses, and although it was bound for the Sun, it could not simply fall straight inward. It had to take the long way around. Solar researchers had spent decades watching our star from the same basic vantage point, here, near the plane where all the planets circle. The solar system was born from a collapsing cloud of gas and dust that spun faster as it shrank, flattening into a disk. From that spinning disk, the Sun ignited in the center, and the planets formed in the surrounding material. They kept the memory of that origin in their paths. Almost all of them orbit within the same thin sheet of space, a plane we call the ecliptic. From this plane, we see mostly the Sun's equatorial regions, the true north and south poles of the star, the places where its magnetic field lines dive inward or spring outward differently are hard to view directly. Ulysses was designed to change that. It would be our first probe to look at the sun from above and below, to see the polar regions that our usual perspective hides. To do that, Ulysses needed help. Rockets from Earth could send it outward, but to tilt its orbit steeply out of the plane of the planets would have taken more energy than we could easily provide. Instead, mission planners turned to a familiar ally, Jupiter. The spacecraft was sent on a path that first carried it far from the sun toward the giant planet. As it approached Jupiter, it flew over the planet's north pole, letting the enormous gravity there bend its trajectory downward beneath the plane of the ecliptic. With that single, graceful slingshot maneuver, Ulysses was redirected into a polar path around the Sunday. From this unusual orbit, Ulysses could look down at the sun's poles and sample the solar wind in regions we had never directly measured before. Over the years, as it looped around the sun again and again, the probe revealed a star that was even more changeable than we had understood. It confirmed that the sun's large-scale magnetic field reverses roughly every 11 years, flipping its north and south in a long, slow rhythm. It also found that the solar wind flowing from the more dynamic southern polar region was, at times, faster than the wind from nearer the equator. Yet, when scientists tried to pin down exactly where the South Pole was in the data, it refused to be a simple, fixed point. The sun's magnetism is not like the tidy bar magnet we might picture. It is a tangled, shifting structure, twisted by differential rotation and boiling plasma. On Ulysses's charts, the South Pole was more a restless zone than a sharply drawn spot. The only thing completely clear was that the sun keeps changing, its fields and flows never quite repeating themselves from one cycle to the next. After learning to look at the sun from above and below, heliophysicists, scientists who study the sun and its influence, wanted to solve another problem of perspective. From Earth, we can only ever see one face of the sun at a time. As the star rotates, sunspots and active regions form on the far side, hidden from our view, then slowly spin into sight days later. Because sunspots and their associated magnetic structures are key indicators of space weather flares, eruptions, and storms, it would be useful to know what is gathering just beyond the edge of our view, like hearing distant thunder before the clouds arrive overhead. To address this, another pair of spacecraft was launched. A Delta II rocket carried the STEREO mission, Solar Terrestrial Relations Observatory, into space in 2006, releasing two almost identical probes into slightly different paths around the Sunday. One spacecraft was placed in an orbit just a little closer to the Sun than Earth, so it moved slightly faster and gradually pulled ahead of our planet. The other was set into an orbit a bit farther out, moving more slowly and falling behind. With time, the angle between their lines of sight and Earth's grew. Each year, the two craft separated by roughly 44 degrees, giving them increasingly distinct views of the sun's surface and surroundings. Because the sun rotates, active regions that are hidden from Earth at one moment can be seen clearly by one of the STEREO spacecraft at another. The pair together offered something we had never had before, a nearly full 360-degree view of our star. This all-around sight is more than a curiosity. When a coronal mass ejection leaves the sun, it does not broadcast a neat label stating where it is headed. By seeing eruptions from multiple angles, STEREO helps scientists reconstruct their true direction and speed, like watching a wave roll across a pond from different positions along the shore. Most CMEs flare out in directions that miss Earth entirely, sailing harmlessly through deep space. But some are aimed more closely at our orbit, and those can compress Earth's magnetic field, induce currents in the ground, and cause substorms and disturbances that ripple through power grids and satellite systems. With the information provided by stereo and other solar observatories, agencies can issue space weather bulletins, warnings and forecasts that allow satellite operators and grid managers to take protective steps. In a world increasingly woven together by electricity and communication, those quiet, technical warnings are part of how we keep the sun's wilder moods from catching us completely unprepared. Long before these sophisticated eyes were put in place, observers had noticed that auroras, the dancing lights near Earth's poles, sometimes behaved in puzzling ways. On many nights, they would glow steadily, linked to large solar storms that stirred the upper atmosphere and kept the polar skies lit for days. But at other times, something quicker and more abrupt would happen. The auroral curtains would suddenly brighten, their movements growing more rapid and intricate, as if an unseen hand had shaken the strings of light. These short-lived intensifications did not match the slower, broader patterns of major solar storms. In the 1,960 seconds, as communication satellites in geosynchronous orbits became more sensitive and more numerous, they began to record sudden, localized drops in the strength of Earth's magnetic field. Those dips seemed to occur at the same times as the quick auroral brightening scientists were starting to call substorms. There was a sense that something in the tail of Earth's magnetosphere, the region stretched out on the night side by the solar wind, was snapping and rebounding, but the details were hard to catch. To study these events more clearly, NASA launched another mission on a Delta II rocket. As its engines lit and the rocket rose through the atmosphere, it carried not just one spacecraft, but a small constellation of them, the Venus satellites. Their name drawn from a long acronym, but also evoking the Greek idea of order and balance. Their purpose was to watch how Earth's magnetic environment responded to changes in the solar wind, and to tie those changes to what was seen in the auroras above the northern polar regions. Each Themis satellite carried an array of long, delicate booms, antenna-like extensions that could measure the strength and direction of electric and magnetic fields around the spacecraft. Over several months, the satellites were maneuvered into elliptical orbits of varying shapes, each one reaching a high point on the night side of Earth. From those vantage points, spread out along the stretched magnetotail, they could sample conditions at different distances, like instruments placed along a river to watch where currents accelerate and where eddies form. The Earth's magnetic field usually diverts most of the plasma from the Sun, channeling it around our planet in a teardrop-shaped cavity. On the day side, near the Sun, some charged particles can spiral down along field lines into the polar regions, where they collide with atoms high in the atmosphere and create the familiar glows of the aurora. On the night side, the solar wind pulls the magnetic field lines back, stretching them far into a long tail. Sometimes, when the tension in those stretched lines grows too strong, they rearrange themselves in a process called magnetic reconnection. Field lines that were once separate break and join in new combinations, releasing stored magnetic energy and flinging plasma along the reconfigured paths. When this happens in Earth's magnetotail, the newly accelerated particles rush back toward the planet along magnetic funnels that guide them into the polar atmosphere, triggering sudden brightenings in the auroral curtains. In February 2008, Two of the Venus probes happened to be in just the right positions to capture such a reconnection event. Their instruments recorded a sudden change, a rearrangement of the magnetic field, and a burst of flowing plasma in the distant tail. 96 seconds later, barely more than a minute and a half, ground stations watching the sky in the North American Arctic saw the aurora leap into greater brightness and motion. For the first time, scientists had a clear, coordinated view linking the invisible dynamics in the magnetotail to the visible dance of light overhead. The loops and arches seen bursting from the sun's surface in images from observatories, those giant structures of glowing plasma confined by magnetic fields, are called flux ropes. They are one of the basic shapes that plasma and magnetism seem to favor, both on the sun and in places like Earth's magnetotail. In them, field lines twist together into bundles, carrying currents and energy. When they form, evolve, and sometimes snap, they help shape the storms and substorms that ripple through space. In that way, the story loops back, from Ulysses diving above the solar poles, to Stereo watching eruptions from all sides, to the Miss listening to the pull and release of Earth's stretched magnetic field. All of these missions, in their own orbits and with their own instruments, are part of a single, quiet effort to understand how a star of plasma and magnetism reaches out across space, and how its changing moods thread themselves through the thin, protective bubble in which we live. The glowing plasma we see bursting from the sun does not move at random. It follows invisible paths, tracing out helical magnetic field lines that twist and spiral around a central core like strands of light wrapped around a rope. When you look at those great loops and arches in high-energy images, you are really seeing charged particles being guided by magnetism, forced to dance along tracks they cannot leave. The Themis satellites and other missions like them helped show just how far this order can reach. They discovered that these magnetic structures, flux ropes, can sometimes stretch all the way from the sun to Earth's upper atmosphere, like long, taut cords connecting star and planet. Along those cords, currents as high as 650,000 amps can flow, a river of electric charge threading through the darkness between worlds. Even with all this progress, heliophysicists, the people who devote their days and nights to understanding the sun and its influence, remained puzzled by some of the most basic questions about the star's outer atmosphere. They knew that magnetism had to be important. They saw loops, ropes, and waves in every image. But the exact way in which magnetic fields heat the corona and fling plasma outward at such high speeds remained stubbornly out of reach. To probe this mystery more closely, a new spacecraft was built, a small focused probe called IRIS, the Interface Region Imaging Spectrograph. Compared with some of the grand missions that carried dozens of instruments, IRIS was modest in size and design. It consisted mainly of a telescope, an imaging spectrograph to split light into its component colors and measure the motion and temperature of plasma and the support systems needed to keep them steady and pointed. It was relatively inexpensive to build and to launch, more like a precise, sharp tool than a large, complicated laboratory. IRIS was placed into a polar orbit around Earth, a path that carried it over the planet's poles and gave it repeated, uninterrupted views of the sun, free from the cycles of day and night that limit ground-based telescopes. Its optics were tuned to look at a very specific region, the edge of the chromosphere, where the plasma of the lower atmosphere begins its steep, puzzling climb in temperature toward the corona. This narrow boundary, where conditions change quickly with height, is where many of the unanswered questions reside. The images Iris returned were astonishingly detailed. Structures that had once appeared as blurry smudges now resolved into fine threads and jets. Rapid changes that had previously been smeared together in time could be separated into distinct events. Among the most striking features it revealed in high clarity were the spicules, thin, waving jets of plasma that shoot up from the sun's surface like countless tiny fountains. At any given moment, there are thought to be around 10 million spicules scattered across the solar surface. Each one can grow to a height of about 10,000 kilometers, reaching out from the photosphere into the lower corona. Yet their lives are fleeting. Many of them rise and fall within just 5 or 10 minutes, appearing, growing, and collapsing in a constant, restless cycle. Seen as a whole, the sun's surface is covered in these brief, upward flickers, like grass blown by a wind we cannot feel. Researchers built computer models to try to reproduce what Iris was seeing: spicules that shoot up suddenly, reach impressive heights, and then fade away on short timescales. The simulations that matched the observations best tended to involve interactions between charged particles and neutral atoms in the plasma, all threaded through tangled magnetic fields. In these models, the push and pull between different components of the gas, combined with the complicated geometry of magnetism, can launch plasma upward, converting magnetic energy into motion and heat. Nothing is completely settled yet, but the evidence suggests that magnetism plays a central role in heating the solar corona and in hurling high-speed jets of plasma into space. The exact mechanisms, how many types there are, how they interplay, how they change with location and time, are still not fully understood. We can see the patterns and build models that echo them, but the deep simplicity that often hides beneath complex behavior has not quite revealed itself. As all this work continues, the sky around Earth is busy. At least 20 different satellites are currently monitoring the sun and its effects in one way or another. Most of them circle our planet, peering outward through the thin shell of atmosphere to watch for flares, ejections, and waves in the solar wind. This vantage point, about 150 million kilometers from the sun, is good for many things. But for some questions, it is not close enough. Heliophysicists know that the particles in the solar wind change character not long after they leave the corona. As they flow outward, they expand, cool, and interact with waves and magnetic structures. By the time they reach Earth, their original fingerprints are partly smudged. If we could sample those particles closer to where they are born, we might be able to tell which regions and processes in the solar atmosphere are responsible for their extreme temperatures and ultra-high speeds. For a long time, that was more a dream than a plan. The regions of space scientists wanted to visit near the sun were simply too hot and harsh for any spacecraft we could build. Instruments and electronics would fail quickly under such conditions. The team behind the Messenger mission to Mercury had already begun to nibble at this challenge. To keep their probe alive in the intense sunlight near the innermost planet, they used a woven ceramic sun shield that always had to face the sun, casting a protective shadow over most of the spacecraft. Around 2010, engineers and scientists started a more daring project, a mission originally called Solar Probe Plus, designed to fly to within about 6 million kilometers of the sun's visible surface, dipping right into the lower corona itself. To succeed, many different systems would have to work together, each protecting the others. The heart of the design was a thick carbon composite heat shield, surfaced with a highly reflective layer of alumina. This shield would always face the sun, throwing back most of the incoming energy and keeping the rest of the spacecraft in its shadow. Because the Sun is a powerful radio source across many frequencies, and because the probe would be so close to it, communication during the tightest approaches would be extremely difficult. The spacecraft would have to operate autonomously while near perihelion, making its own decisions about pointing and protection, and only later, when it had moved farther out again, turn and send its stored data back to Earth. In 2017, the mission received a new name that carried a quiet resonance: Parker Solar Probe, in honor of Eugene Parker, the physicist who had first proposed the idea of the solar wind decades earlier. It was the first time a NASA spacecraft had been named after a living person. Parker himself, then in his 90s, spoke about the mission with a mixture of curiosity and humility. On a journey into such new territory, he said, "You have to expect surprises. They might be small or they might be large, but they will almost certainly force you to adjust your point of view to fit what the data actually shows." He also returned to the coronal heating puzzle that had occupied him and many others for so long. How could the corona, the Sun's outer atmosphere, reach temperatures of 1 million or 2 million degrees Kelvin when the visible surface below sits at about 5,600 Kelvin? It clearly isn't just warmed by the sunshine coming from beneath. Something else is depositing energy there, and we will not know exactly what until we have measurements from up close and time to think carefully about what they mean. The Parker Solar Probe itself is not a large spacecraft by modern standards. Its launch mass is under 700 kilograms, modest compared with some planetary orbiters. Yet to send it on its demanding path, one of the most powerful rockets available was chosen: the Delta IV Heavy. The reason is that to get close to the Sun, you must, in a sense, undo much of Earth's orbital motion, dropping inward toward the star, rather than simply being flung outward. In the pre-dawn hours of the 12th of August 2018, the final countdown ticked away at Cape Canaveral. Eugene Parker was there in person to watch, wrapped in the early morning dark and the anticipation of a lifetime's work turning into motion. When the engines lit and the rocket rose, the bright plume cut a path through the humid air, carrying the small probe toward the vast brightness it would one day skim. The mission plan called for Parker to complete 26 highly elliptical orbits around the Sun over about 7 years. To reach the desired path, it would make 7 close passes of Venus, each one using the planet's gravity not to speed up, but to slow down and lower its orbital distance, allowing it to sweep closer and closer to the Sunday after. Separation from its upper stage, the spacecraft first deployed its solar panels, those delicate wings that would provide power. Near the Sun, they would be partially folded back, with a dedicated cooling system carrying away the heat that still reached them around the edge of the main shield. At the rear of the craft, a boom carrying magnetometers, sensitive instruments to measure magnetic fields, was unfolded, moving the sensors away from the spacecraft's own fields. Antennas to measure electric fields and waves in the plasma were extended, snapping into place like the feelers of an insect reaching into its environment. Though Parker left Earth at high speed, its job was not to race away into the outer solar system, but to fall inward. Each flyby of Venus gently robbed it of some orbital energy, reshaping its path. As it arced closer to the Sun, gravity would accelerate it to astonishing velocities, up to around 720,000 kilometers per hour at its fastest. On the outward legs of its orbits, it would slow again, only to plunge faster as it descended on the next, even closer pass. Just 52 days after launch, Parker made its first close approach to Venus. A month later, it approached the Sun for the first time. During each of these deepest dips into the corona, the probe would be out of contact with mission control for about 11 days, the Sun's radio presence overwhelming its ability to talk to Earth. In those quiet intervals, it would simply do its work, keeping its shield pointed precisely at the Sun and recording the behavior of particles and fields around it. The heat in these regions is intimidating, but heat in space is not quite like heat in air. The particle density near the Sun, even in the corona, is far lower than in Earth's atmosphere at the surface. The few particles that do strike the shield carry immense energy, and the radiation is intense, but with the right materials and design, the spacecraft can survive. At the front, the shield may reach temperatures around 1,500 Kelvin, glowing fiercely. Behind it, in the calm shadow, the protected electronics can remain near room temperature, quietly ticking and listening. Once Parker swings away from the Sun, on each orbit, it can re-establish radio contact. Then, bit by bit, it plays back the data. It has stored measurements of the solar wind, magnetic field structures, waves, and particle distributions from regions no spacecraft has visited before. Among the early treasures was the first image taken from within the Sun's corona, a view of a coronal streamer, a bright, elongated structure of plasma extending outward, captured from the inside, looking out. In the same image, a bright point marks the planet Mercury, while some dark spots show up as correction artifacts from the camera. The probe's second and third close passes were at distances and speeds similar to the first, building a baseline of measurements. With each subsequent orbit, as Parker continues to use Venus to reshape its path, those passes will be both lower and faster, cutting deeper into the Sun's atmosphere and sampling regions closer to the roots of the solar wind. In 2024, Parker's solar probe is scheduled to fly past Venus for the last time. After that, its final 5 close passes by the Sun will bring it to within about 6.2 million kilometers of the visible surface, closer than any spacecraft has ever gone. By the time those orbits are complete, we expect to have a much clearer picture of how the corona is heated and how the solar wind is accelerated to such remarkable speeds. But each answer will almost certainly raise new questions, opening further layers of complexity in a star we once thought of as simply a bright, steady disk. Already, a clearer understanding of the Sun has led engineers to change the way they design satellites and manage power grids and communication systems. Knowing more about the storms that sweep through space allows us to shield our machines and anticipate disruptions. And as plans grow more concrete for sending humans back to the Moon and eventually outward on planetary journeys, the need to understand this space weather becomes more personal. The same star that warms our days also sends out bursts of radiation and streams of particles that can be hostile to fragile bodies and electronics. Somewhere between admiration and caution, we are learning to live with that duality, to take comfort from the Sun's steady light, even as we study its tempests, preparing ourselves for the times when our quiet, orbiting home is brushed by the wilder edges of the star we call our own.